Hello and welcome. In this video, we'll be deriving the quadratic formula with a geometric focus. Of course, naturally we'll have to do some algebra, but I hope at the end of this video, you'll also have a good geometric understanding. To start with, we'll be working with the real numbers, or if you want, the complex numbers. What this means is that we're going to have all of the coefficients to be real or complex numbers. We will not be going into the complexity of this or talk about the fundamental theorem of algebra. So let's start. In particular, what is the quadratic formula? It's a polynomial where the degree is 2. The general format is ax squared plus bx plus c. Note that we always make polynomials equal to 0. The goal is to derive the quadratic formula. To do this, let's first analyze what the quadratic polynomial represents. First, the real number c is just a number. It can represent anything, a line, position in space, or area, literally anything, which is the beauty of mathematics. In particular, let's just say it's the area of some polygon. Next, let's look at what bx represents. Well, remember that bx is b times x, which is a rectangle of length b and width x. Now, let's look at a more complicated one, ax squared. Recall that every real number, if we square the square root of itself, we get back the number. In particular, we have that ax squared is actually the square root of a times x, all of that multiplied itself, which is square root of a times x, which now we know is a square with sides square root a times x. Now that we have a geometric understanding of what the quadratic polynomial represents, let's analyze the square that has sides length of x plus k. That is x plus k squared. Let's separate the x plus k respectively, which gives us this partition of the square. We now have two squares, one with sides x and the other with sides k, and the two rectangles of length k and width x. Algebraically, this looks like this. With this identity, we want to force our quadratic polynomial to mimic this construction. So back to our general case, we note that we can always divide by the leading coefficient a, giving us this new form, given a isn't 0. Looking at this, we see clearly that the constant c over a isn't the square of the second coefficient. Thus, we'll simply move it to the other side of the equation. This is where we get to the tricky part. The identity that we looked at before, we saw that the second coefficient must multiply by 2. So we artificially add this 2 in, and we do it by multiplying by 1. Note that any number divided by itself is 1, so actually we're multiplying it by 2 over 2. Thus, our new form looks like this. Geometrically, what we have now is a square with sides x and two rectangles with length b over 2a and width x. Thus, we want to add in the square with sides b over 2a. That is, we want to complete this square. Algebraically, we have this. Now that we have a square, we can represent our polynomial as a square. From here, we start doing some good old algebra. First, we reduce the right-hand side. Take the square root and then isolate the x. And voila, we are done.